What I'm going to be talking about is why machine learning, lithofacies prediction, is transforming, and I believe it will transform reservoir characterization. And I'm going to start with some observations and conclusions. And first, we're going to see that the machine learning lithofacies prediction is not a black box. It actually extends our current workflows beyond human capabilities. You're going to see that the same or one of the workflows that we have been using for years is actually expanded by using machine learning. The other observation is that it breaks with lengthy, analyst-intensive model-based processes. What this refers to is, to say an example, is the seismic data. When we do elastic inversion, we require the data, the seismic data, to be fit to a model. This model is usually the Sopritz equations, or one of its if it or one of its different forms, like Aki and Richards, for example. In doing that, the processor spends a lot of time trying to make sure that the seismic data fits that particular model. And it's not uncommon that, we do the processing, we do the inversion in one or two wells, it doesn't tie, we go back, recondition the seismic data, do it again, and that turns to be very, very lengthy. This is just one of the processes that is model-based. Another is the convolutional model. We have to make a wavelet and then try to remove the wavelet. So that's also a lengthy process. Tying synthetics to seismic can take, months, depending on the number of wells and the complexity. And then finally, what we're going to see is that the results are easy to interpret and are obtained faster than with conventional workflows. I probably forgot to mention in here that the process that we use does not require or does not use model-based processes. We still require good quality seismic data, but the processing sequence does not has to be as demanding as a processing sequence aimed at AVO or inversion. So here is to the last point, the ease of interpretation. Here I am showing in the left the seismic data. Then in the middle section here, it's the seismic data with the seismic trace extracted. Sorry, the seismic trace extracted in the left track. Then we have the petrophysical evaluation. Here we have the solid minerals. Here we have porosity, water saturation, and here we have a lithofacies log. In this case, we have here the pay sand, which matches, you can see here, matches a relatively clean sand, low shale, low water saturation, high porosity. So we have this as the lithofacies pay sand. We have lime. A lot of the section is lime, and then we also have shaly lime in yellow orange. And when we do the process, after doing the process, we can see that we can transform the seismic from this image into this image, where we can see, you see here a layer of shale, matching a layer of shale in here. We have the wet sand, matching the wet sand in here, the pay sand, and then finally over here another thin layer of shale. So again, the interpretability of the section obtained is considerably better than what I am used to see from inversion. Additionally, you can see incrementing or increasing the interpretability or resolution in the vertical direction also increases the interpretability in the horizontal direction. Look at this fault here. We have the fault in here, but we have it a lot better defined in this section. So we're going to see how is the process that we follow to go from the seismic into the lithofacies prediction. And that the workflow consists of taking two independent data sources. From one, we have the seismic data, and from the other one, we have the well data, and then merging these two sources through cross-tabulation. So we're going to start with the seismic data, and we're going to create self-organized maps. These maps take several attributes and forms clusters in multidimensional space. The attribute selection for this process can be done in several ways. In Paradise, we have two two processes. One is principal component analysis, which is dependent only on the seismic data, and recently introduced is mutual information, in which the attributes measure their correspondence, or how they are related to the well logs. And that way we can select the best attributes to obtain a particular lithofacies log. So we're going to talk more about the self-organized maps. And we like them, or you use them, because, as I was saying, they are multi-attribute clustering in multi-dimensional space. And I would like to illustrate how they work, or their use, with a simple crossplot. And many of us have seen this type of crossplots where we have two attributes, in this case, or two rock properties, in this case P and S impedances, and we select the area in which the reservoir property of interest is located in this crossplot. In this case, we have here porosity, and then here we have in blue what corresponds to shale. So we can differentiate the very good quality reservoir. But if you look right here, we have points that have the same P and S impedances for both the reservoir and the shale. So there's ambiguity. A single point represents the reservoir and represents as well the shale. One way of reducing that ambiguity is to uh, add another dimension. In this case, the third dimension is density, and we can see how now we can differentiate a lot better what we consider reservoir. This is good. We added another dimension, and we can separate better. Nevertheless, in here we still have non-uniqueness. What that means is that a single point, a single three-dimensional sample, let's say a point in here with a given density, P impedance and S impedance, can be obtained with several combinations of lithology, porosity, and fluids. And here is an easy example, or a simple example, simple model, consisting only of B shale, water saturation, and porosity. This is a well from South Africa that was used to model this type of response. And what this is saying is, right here, I am selecting a P impedance of 9.9 and S impedance of 6. And then I see what petrophysical properties can be used to obtain this particular set of rock properties. And what we find out is that we obtain these properties when the rock has 12% of porosity, 18% of B shale, and 38% of water saturation. And the exact same properties, or the exact same values of P and S impedance, are obtained when we have 14% porosity, about 10% B shale, and 98% or 95% water saturation. So this is very, very ambiguous, very non-unique, and it's related to trying to obtain three petrophysical properties using only to rock properties. And the obvious way forward, or reduction of non-uniqueness and ambiguity, is to increase the number of attributes. Okay, but now you're going to say, listen, I'm already working with three attributes, three rock properties, three dimensions. If I add one more, I won't be able to make an interpretation. If I have 5 or 6 attributes, I mean, it's beyond my human capability to identify clusters. But that is exactly what the self-organized map do. What it does is that it's going to take several attributes, 10, 15, 8, whatever number of attributes, and it's going to cluster those in multidimensional space. So I'm going to try to illustrate how this is done, but before doing that, let me just a quick reminder on how the crossplots are created. We have here a two-dimensional sample formed of a value for P impedance, a value for S impedance, P and S impedances, and in this case, the color is the porosity. What sum does is very much the same. In this case, instead of having a two-dimensional sample, we are using 8 dimensions. We are taking 8 attributes. So this is an 8-dimensional sample. And this 8-dimensional sample, we are going to assign it to a cluster. Let's say I'm going to assign it to cluster 824. Then it's going to do the same for the next sample, and the next sample here gets to this sample. This sample is similar to this one, so it's going to assign it to cluster 824. In the end, what we are seeing here is 144 clusters identified or selected in an 8-dimensional space. Uh, and this is how this would look in the real seismic. Here we selected 81 clusters in a 7-dimensional space, and each one of the samples now corresponds to a particular cluster location. So we're transferring samples in time to clusters. Now, the next step is to assign here. These are nice colors. The next step is to assign lithofacies values to each of these clusters. Right now, all we know is that this is cluster, the blue cluster or blue neuron with number 81, and we want to say what lithofacies that corresponds to. And that is done using a lithofacies log. There are several ways of obtaining lithofacies logs. In Paradise, there is the option of obtaining with cutoffs using k-means, which is another machine learning technique, or we can read from LAS files. And these lithofacies logs are then going to be matched or merged with the sum through cross-tabulation. What we mean by cross-tabulation, right here we have the petrophysics. This is the lithofacies log. This is the self-organized map extracted at the well location. And what we mean by cross-tabulation is that we are going to count how many samples of each of the lithofacies, if each of the lithofacies, remember this is gas sand, brine, clay, and shaly lime, I believe. How many of each of these lithofacies matches each of the neuron? That is, we're going to count, in this case, for example, neuron 1 matched lithofacies lime 826 times, clay lime 40 times, clay 5 times, etc., etc. And so this is the contingency table. Here we are going to display it as well, or for QC we display it as well in the stack bar chart. Here we see this is 126 samples, this is 40 samples, 5 samples, and then we are also going to transfer these colors to a lithofacies topology, also called the Chaveste honeycomb. And so what we do is here, this is the most number of samples corresponds to lithofacies lime. So we're going to assign lime. The same for neuron number 2. We can see here number neuron 79 is mostly gas sand, so we assign it gas sand. Now you can see that the tones are different. For example, this is darker red than this here, and that indicates that this has a higher probability that of being a gas sand than this being a gas sand, and that is computed simply by taking the number of samples of the pay sand in this case divided by the total number of samples in that neuron. The next step is now to well, before doing that, before showing the example in the seismic, let me mention that we have here the contingency table, and from here we can do a lot of QC on how the lithofacies from the well matched lithofacies from the seismic. Here, for example, I am showing the confusion matrix reduced from the contingency table. And here I have the distribution of well logs and seismic prediction. Here we can use the confusion matrix for QC of these two pie charts. We can see here that the clay lime appears to be off, right? I mean, this is too much clay lime compared to what we have in the well logs, and that is also represented in the confusion matrix. What appears to be happening is that the clay lime and the lime have the same rock properties and they are difficult to differentiate. So if we wanted to make something that is more robust, we can then merge the clay lime with the lime. Taking note, of course, that this does not modify our property of interest, which in this case would be the pay sand. Another tool, another way of QCing this is by noting that there's too many, or there's a lot more samples of lime than any other of the lithofacies, and we can normalize the count of samples, and we can obtain something that is a lot more reasonable of what we would expect. Right here, this is the number of coincidences. So when we have high number of values for the diagonal, that means that our lithofacies from seismic are matching the lithofacies from well log. So again, these are tools that can help us identify the optimum lithofacies. Also, we have a Kramer's V, which is a value of association in between the phases from well logs and the phases from seismic. So in the end, this is what we start with. We have here the seismic. This is the self-organized map. And then after doing the lithofacies prediction, the cross tabulation, we end up with the predicted lithofacies. And again, this is not based on deterministic processes. It's purely statistics. And if you notice here, I think that the cleanliness and the definition of this formation would be hard to obtain with any type of inversion. Note as well the resolution that we're getting. Right here is the seismic. We are looking for, I'd say, less than an eight, maybe in between a fourth and an eighth of the wavelet, and yet we are having a very, very good definition. Okay, and just to conclude, and I would like to go back to my observations and conclusions with which I started. And we see that it extends, the workflow that I presented extends the current workflows beyond human capabilities. That is, we can find clusters in 8 dimensions, 10 dimensions, in more than 3 dimensions. We see that it breaks with lengthy analysis-intensive model-based processes. This is not the deterministic process. And then finally, we see that the results are easier to interpret and are obtained faster than with conventional workflows. And with that, I finish my presentation.